So it's my great pleasure to be speaking here. Thank you to the organizers, and a very deep thank you to Elisha. So it's only the 7th time that you hear about someone raving about Elisha, so I feel confident to do that at least once more. So I met Elisha a bit more than 10 years ago, and I cannot express how much it counted to me. Let me just say that since this meeting, we collaborate on at least 6 papers. So I hope this is a testimony of fruitful conversation and not of me exploiting insights of Elisha. That's not clear. So I will be speaking about a notion that we propose with Pierreville and Elisha. So that's one of the 6 papers. And okay, it is inspired by other notions that I will speak about. And it is slimness in the 3 sphere. So I'm also grateful to all the speakers before me, especially Anna, John, Raphael. Since they have already done my introduction, I will just do my introduction anyway, but maybe you will be able to understand it. So the beginning is very much alike to the one of Anna. So let's begin slowly. I want to speak, well, maybe before the beginning, the plan of the talk, I will speak about R circle, C circles, and the foliation. The foliation of the sphere. Then I will try to give some insights on how to deform the situation I would have described in the first part, and then a discussion of slim limit sets. There is a secret 4th part, but I'm not sure that I will be able to talk about that. So the first part is a description of a classical point of view on the 3 sphere and R circle and C circle. And if you just understand the first part, I will be very happy because you would have understood a nice geometric construction. So try to stay with me at least for the first part. Then you can just leave. So, as you at least now know, inside H2C, you have 2 kinds of totally geodesic planes, well, 2-dimensional objects, which are H1C and H2R. And we can look at the intersection with the boundary at infinity of H2C. So for me, it's too long to write every time boundary at infinity of H2C. So this will be the 3 sphere. Every time I will write S3, it is this one, not another one. I don't care about other 3 spheres. So the intersection can be C circles, and I will redo the picture Anna did, and the counterpart are R circles. So maybe in order to do picture, I have to take a model, and I will take the model where the 2-1 form is given by this formula. If you prefer the matrix of the emission form is this one. Okay, I put a true, don't be too much puzzled by these two. It's just to avoid some square root of 2 appearing now and then. So, but it is a 2-1 emission form. And in this model, the boundary at infinity, so the Swiss sphere, so it sits inside CP2, this construct, the projective model, so maybe I have to write down some things. H2C identifies, or maybe is defined as a set of vector of class of vectors V in CP2 such that okay, I will put a transitory notation I will not use that much, whose norm for this form is negative. This is well defined. This condition is well defined for a projective vector. So in this model, just
there's something wrong there. Yeah. What I either want to minus
what I want, sorry.
I think you want the 2 on the here and the plus.
Okay, sorry. Thank you. So this is joined with Pierre. He will check everything. For the parameterization I will give here, without the 2, there would be a square root of 2 in this parameterization, and I'm too lazy to write down a square root of 2. You can speak with Elisha about that and how bad an idea it is. So, if you look at the null vector in CP2, there are the vectors which in the affine chart are this form, and there is another vector. Okay, sorry. Z any complex number and T any real number. So all the vectors of this form for Z and T like that, and one point at infinity. So this is called infinity. I write, okay, let me write it in a better way, because I will use that. So vector of the form minus modulus square of Z plus IT in the first coordinate, then Z, then 1. And then a point at infinity, which is 1, 0, 0. So the good thing about this parameterization is that you can draw. You are in R3 as Anna explained before. And so in this model, let me do a picture, and I will do a picture on a small blackboard, and I will take some colors. So C circles are vertical lines or ellipses that project on actual circles. So that was Anna's part. And so these are C circles. And R circles are either line in the plane going through 0 into infinity, or some kind of Pringles-shaped curve that project on a Slimness cut. You can just write down things, and it will give you that. So we will keep in mind this. And okay, another very important object that this situation gives is a CR structure on the sphere. So what is this list? So at each point, in the sphere, I can look at the orthogonal line in CP2. So I will, as Anna did, I will make the real picture and let you pass to the four-dimensional case. Since in the sphere the vector has 0 norm, P belongs to its orthogonal. So, in fact, this line is included in the tangent space to the sphere at this point. This line is a complex line, so it is a two-plane, and the tangent space to the sphere is a three-dimensional space. Okay, this is a three-sphere. So this gives you a distribution of real planes on the sphere in the tangent bundle of the sphere. So it is a contact structure. And it is more than real planes. Those are complex lines. So this is a CR. But I will just give it in coordinates with this model. So those are, okay, I will mix the sign. You know what? I will check. Before Pierre telling me I'm wrong, I will check. I hope that I write it in the right way. So there is a 2 coming from my silly choice of form. Okay, why I care about this CR structure is that you can check very easily with this formula, or I will draw it on the picture, that C circles are everywhere transverse, whereas R circles are everywhere tangent to the distribution of plane. So on the picture, so at 0, the contact plane is the horizontal plane. And you can see on this formula that it is invariant by vertical transformation, vertical translations. In fact, it is this structure by design is invariant by the whole PU21, the whole group of transformation. So here you see that this C circle is everywhere transverse. And as C circles, up to PU21, there is only one C circle. This gives you the first point. And okay, here it's maybe a bit more tricky to see what you can check is that when you go along the complex, okay, we'll do that in this way. When you go along the complex plane, in the complex plane along a line, then your contact plane rotates up to becoming vertical. And then the distribution of plane is invariant by rotation, invariant by vertical translation. So more or less I describe geometrically this contact distribution. It is the usual contact distribution on R3, which is invariant by rotation, up to the 2. And so, okay, so when you see that this line is always inside the plane. So it is always tangent. Okay. So maybe some properties around these things. Okay. 2 points define a unique C-circle. If I take 2 points in the sphere, those are 2 points in the projective space. So I have a unique complex line through these 2 points. And this gives me the C-circles. And you can see in this picture that the only C-circle going through 0 and infinity, if you believe my picture, is the vertical line. It is not true for R circles. And here in this picture, all horizontal lines through 0 are examples of R circles through 0 and infinity. And those are all these R circles through 0 and infinity. A point that will be important for us is that C-circles are naturally oriented. Because those are circles in a complex line. So you have the complex line give you an orientation of the plane, so an orientation of the circles. So there is a natural orientation, whereas there is no such, not true for R circles. Alors, maybe I will say a more precise version of it. If you have some R circle, there is a PU21 transformation acting on the 3 sphere that preserves the R circle but reverses the orientation. So there is no invariant notion of orientation. And I will say something vague, but that will be made more precise later on. Small C circles become tangent, more and more tangent, to the distribution, the contact distribution. What do I mean by that? Is the following picture. Maybe. Look, a C-circle centered at 0 is exactly a circle, an actual circle in the complex plane centered at 0. So it's actually a circle. When I shrink these circles at this point, they define something which becomes tangent to the contact distribution. Okay? So this is just a very vague statement, but that I will try to explain it more precisely later on.
You can also see this from your other pair of points tending towards P lines within.
Actually, that's not true. Because okay, I will talk about that later.
In a specific way.
In a specific way, exactly. In a specific way. So, okay, maybe let's just say that. No, okay, we will speak about that later on. So what is, I said R circle, C circle, those are covered by these properties. Are there any questions on that? Okay, so let's speak about this foliation. Okay, I have the sphere, and I also have the foliation. So what I want to illustrate is that, so let R be a C circle, be a R circle, and R circle. So it is a boundary at infinity of some hyperbolic plane. And let omega be its complement in the sphere. Then there is a diffeomorphism from the unit tangent bundle to H to R. Okay, I prefer to write it in the other way. It is a diffeomorphism, so I can choose anyway. So omega is diffeomorphic to the unit tangent bundle to H to R. And it will be a bit more precise because we will understand under this diffeomorphism what happens to the line of the geodesic flow. Okay, so what is this diffeomorphism? So I will make a picture, not in the model that I chose at the beginning, but in the ball model. So beware, this is a three-dimensional picture, but you should recall that we are in a four-dimensional case. So there will be one dimension lacking. So I have my R circle here. I have my real hyperbolic plane, and I take a point P outside. How can I construct not only a point inside H2R, but also a unit tangent vector at this point? So the point, if you are used to negative curvature geometry, it's quite easy to understand. You just project. Let's call it X. Okay, you do this projection, and this is a real geodesic, so this has a unit directing vector, generating vector. But we are in a complex situation, so we can make the complex structure act. So this is V, and this is JV. In coordinates, you multiply the coordinates of I by J, you multiply the coordinate of V by I. Okay? It is not hard to verify that this vector is actually tangent to H2R. This vector is purely imaginary, and this vector I multiply by I, so it becomes purely real. Okay? This is the morphism. Okay. So now I can try to understand what I told about geodesic flow. So what happens when I follow the geodesic flow in H2R? I have two endpoints of my geodesic, I call A and B. And all this picture, in fact, happens in the line through A and B, because J, the complex structure, preserves this complex line. So everything happens here. And so what we see here is a C circle. But recall that this C circle is oriented. And one can check that with this choice. I hope that I did not forget a minus, but I think that with this choice, the orientation happens like that. So when x is moving from the past infinite point to the positive infinite point of the geodesic, your point P follows the C circles, the rightly oriented arc of this C circle. So I define, given A, B in the sphere, I call the arc A towards B is the half C circle through A and B. So this is a unique C circle oriented, of course, the notation is here to help you, from A to B. Okay? And
Can you describe this?
oh yes, of course. There is one parameter subgroup of a real loxodromic transformation with repulsive fixed point A, attractive fixed point B, and this is the most natural orbit.
You consider open or closed arc?
Open. Okay. And so this picture should convince you that the orbits of the geodesic flow here are exactly in one-to-one correspondence with arcs of C circles of this form, A to B, with AB in the boundary of H to R. So what I say is that consequence omega is foliated by arcs A to B for A, B in my R circle R. So there are a lot of proof of this diffeomorphism. For example, you can this set is also foliated by full C circle, not arcs, but just full C circles. You can compute a line number and see that it is actually the one of the unit tangent bundle and so on. But I like this geometric presentation because, okay, I like negative curvature geometry. And it makes this sentence, well, somewhat easy. Okay, if you want, you can. I've done the general presentation. If you just are convinced by this, I'm happy. And now you can. Yeah. Yeah, you have a question. Yeah, of course. There are. Yeah, no, there are different ways of seeing this, but I want to stick with the main character being the arcs. Okay. Because so I move on to my second part, which is how to deform this situation. So my actual question is that, okay, you have this R circle. I would like to deform it a bit, or not a bit, maybe deform it actually, in such a way that we still have this foliation property. So the question is deforming R to a topological circle, let's say E, such that hopefully, so the question is it possible to deform? Such that the complement of E is foliated by arcs let me put a question mark here, even if it doesn't make sense. So is it even possible? And if it is, do we have some examples? Okay, so there are some quite easy to see constraints. For example, in order for this foliation to be even only possible, you have to ensure that these arcs are not meeting once more E, because okay, these arcs are supposed to foliate the complement. They should be at least included in the complement. So first condition, which is called hyperconvexity, which is a really fancy name for this simple condition, but the name comes from actually one of the inspiration of this work, a work from Positive Sambarino-Winart on another representation. So, but okay, if you don't know anything about that, this is a very simple definition. E is hyperconvex for this setting if no C circle hits E 3 times. Okay, a C circle can hit my set 0 times, 1 time, 2 times, but not 3 or more. This condition ensures that those arcs are indeed inside the complement. Seems a harmless assumption to do. But then there is another assumption a bit more difficult to state. So I want to speak about horizontality. Horizontality. Okay, in some sense, maybe I won't be very convincing for that, but I want this set E to share some property with the R circle, which is the fact that it is tangent to the contact distribution. In fact, if it is not tangent, maybe you can have a foliation, but some arcs are very, very parallel to the set and it becomes a mess. So I want to say that my set is somehow tangent to the contact distribution. The problem is that my set is just a topological circle. So it's kind of hard to come up with the right definition, and we propose this definition. So maybe, I forgot the Cartan invariant. Okay. Anyway. So I will first define the line map, which is a very simple map, but which helps a lot. So whenever you have 2 points in the sphere, okay, you can look at the real hyperbolic picture that I erased. You can take the point which is orthogonal to the line PQ. So let me redraw the real hyperbolic case. If I take 2 points here, P, Q, this is a line in the real projective space, plane, and this line has an orthogonal. Okay? There is a 2-1 form. I call this LPQ. Okay, but I want really to define L on the Cartesian product of 2S3. So I have to decide what to do if P equals Q, and you have guessed. When I have only a point, I have only one natural complex line, which is the orthogonal. And if what is the point orthogonal to P orthogonal? It is P. Sorry, P. Well, let's take it like that. L of PP equals P. Okay, so this is a map defined on the S3 times S3. Beware, it is not continuous. And I will just wave hands with a picture above. Okay, so I have said that at this point, okay, how to say that? Okay, well, I will take P equals that, and take a sequence of points Q equals this one. Okay? The line, the complex line generated by P and Q is constant. It is the line whose C-circle is the vertical line. The C-circle between P and Q does not depend on Q when going down vertically. So when I do the sequence of L of PQ in this way, I have just one constant point, which is not P orthogonal. Okay? In order to have LPQ go to P orthogonal, I have to take Q going more horizontally than vertically. You can write it down explicitly in coordinates. But it is not continuous. If Q goes to P along a C-circle, the limiting point of LPQ will be the orthogonal to the C-circle. If Q goes to P along the contact distribution, then the limit point will indeed be P. And so these line maps, or the continuity of these line maps, measures, in some sense, that convergence happen along the contact distribution. So definition, a set E inside the sphere is horizontal if the line map restricted to this set is continuous. And I don't need smoothness for this definition. I just need subset. Okay. So maybe I should speak about slimness before the end of the talk. Okay. So slimness is a quantitative version of both hyperconvexity and horizontality. Note that hyperconvexity is, in some sense, a global property. You are looking for 3 points, for configuration of 3 points that maybe are far away one from each other, if it makes sense to say that. Instead, this condition is very local. It's about convergence of pair of points. Well, okay, so slimness. Recall the Cartan invariant. I can say recall because it has been defined once. Maybe I don't remember if Anna actually defined it, but okay. The Cartan invariant of 3 points. So I will only stick 2 points in the sphere. In fact, I'm not able to do complex hyperbolic geometry. I just know how to do a bit of CR geometry. So I should put the minus sign at the right place. Okay, whenever I have 3 points, okay, I cheat a bit. Those are lifts inside C3. Those are points in CP2. I lift inside C3, sorry. I make this triple product and compute the argument. This does not depend on the lifts, as you can easily check. And for convention, in order to state things a bit easier, if P, Q, R are not distinct, in fact, well, this definition only works for distinct point, because if P equals Q, this product is 0, so the argument of 0. If it is not distinct, for this talk at least, we will just put 0. I mean, well, okay. Let's do it this way. And the main property is that this Cartan invariant, it is a complete invariant of triples of points, and as such, it detects if points belong to 1 C circles or 1 R circles. So if you are in the real case, the argument is 0. Makes sense. And if you are in a completely complex case, then there is 1 C circle. Well, you can say for the C circle case, you can say that R is inside the C circles for P and Q.
It depends on the beam. You have 2 of them the same.
You're right. You're right, you're right. Okay. So, now, definition of Slimness. A set E, so fix some angle positive and smaller than pi over 2. This will be a Cartan invariant. So, who is losing on me? My set E is alpha slim, and if I don't care about the actual alpha, I will just say slim. If for all points in this set, the Cartan invariant is less, well, in absolute value, is less than alpha. Okay, so this is a quantitative version. Well, it is clearly a quantitative version of hyperconvexity. If this happens, no triple of points have Cartan invariant pi over 2, so no triple of points are on the same C circle. It is not so clear that it is also a quantitative version of horizontality, but indeed it implies. Well, maybe I won't prove that. If E is slim for some value of alpha, then it is hyperconvex. This is clear. And horizontal. maybe an example of a slim. An example. First example. An R circle is slim. Okay. I hope that I have another example to show you. Indeed, I have. Okay, this purple is perfect. I can look at what I call bent R circles. So those are the union of two half lines inside C. So let me do a proper picture in the plane. I take the union of two half lines with, of course, an angle theta, and I call it R in this index theta. And if theta is pi, you have an actual R circle. And so the proposition here you can compute. You can compute a Cartan invariant for this example, and you can prove the proposition, well, by ourselves. So this set is slim for this angle, and maybe some kind of not the best result we can hope. Recall that we wonder about deforming the foliation. And if theta is bigger than pi over 2 and less than pi, okay, I can only care about theta between 0 and pi by symmetry. And so I say if the bending with respect to the R circle case is not too big, I have not bended for more than pi over 2, if this happens, the complement is indeed foliative. At least I have a family of examples. Well, I have one parameter deformation of this situation of foliation of the complement. How to prove that? Well, I think you can prove everything if you want. You can prove everything by elementary computation, but it relies, in some sense, you understand more using some deformation theorem that we gave. The following one: if I have a deformation of my R circle, so I will write in this way. I have a deformation with E0, my preferred R circle, once again the same, and there exists alpha such that all my sets are alpha slim. So I deform my R circle, but I ensure that there is a uniform slimness. If you do that, then for any t, the arcs that I consider. Well, they do not quite foliate the complement. I would have loved this theorem, but this theorem is false. But at least they cover the complement. It's not that clear that if you deform your R circle, maybe there are some points far away that you won't hit by arcs. Maybe there is an abstract topological argument saying this cannot happen, but we have not seen this argument, so we have to do a proof of this theorem. At least you cover all the complement. It is not a foliation because arcs could meet, could intersect, but at least you cover. And then in this very explicit case, you can write down the condition for two arcs intersecting and ruling it out under this condition. And if the bending is too big, then you will cover, but it will not be a foliation. There are arcs actually meeting. Okay. How many time we have left? 8 minutes. Okay, so this is an example of deformation, but it is really an ad hoc example. I was hoping to speak about some kind of Hilbert distance defined on this complement and the fact that arcs are quasi-geodesic, but I will skip this part. If you love Hilbert distance, come and speak to me. I love this part. What about limit sets? This was the beginning point of all this work. But in some sense, working with Elisha and Pierre, we found out that it was actually easier to drop the invariance property on our slim circles, just speak about general slim circles, proves this kind of theorem on general deformation of slim circles, and then look at the application to the case where these circles are limit sets. Why is this? This is a very natural question to ask, because there is a theorem, or maybe a proposition in this case. I don't know. So let's say, take gamma be the fundamental group of a compact Orbi surface. If you don't like about Orbi, just forget about it, but I would like to speak about triangle groups. So okay. But it is compact. This is important. Okay, so, and we look at the space of representation of gamma inside PU21. And, okay, so I will simplify a bit the presentation. I fix once for all gamma as a subgroup, as a lattice in SO21. So I have a first representation, which is the R function representation. So this representation fixes a copy of H2R. On this copy, it acts as in the real hyperbolic case, and then it acts on the complement of this H2. Its limit set it is, of course, it is a boundary of the copy of H2R it preserves, so it is a R circle. Now, when I deform, under the co-compactness property assumption. So when I deform rho 0 into rho, lambda rho varies continuously. And the supremum of all these Cartan invariants I can look at all the Cartan invariants and the supremum, or in this the smallest alpha, the inferior bound of the set of alpha for which we are slim. So this quantity varies also continuously, and this is a result of Potetti, Sambarino, and Winart. You can express it in a lot of different ways. Maybe Olivier would be the best person to speak about that. But so this varies continuously. But you are beginning with this sup being 0. So at least for small deformations, these limit sets are indeed slim circles. Consequence. Something varies continuously, begins at 0, so it cannot hit pi/2 right after the beginning. Okay. So you can apply this deformation theorem. When deforming the limit set, at least the set of arcs covers the complement. So let me give you some illustration. So for gamma, the orientation preserving subgroup of the triangle group 334. So now you know everything you should know about triangle groups. And we have already seen that there is an orientation subgroup, index 2 orientation subgroups. Oh. This is a picture of the foliation. In black, you have the R circle, and in blue, all the C circle with hitting twice the R circle. You have nothing now. Why is that? Okay, I should hand here. Is that good? It's good. Raphael, it's good. No, it's good, it's good. Okay. So, I can speak 2 minutes. What you see here is the character variety of this group, gamma. So what does that mean? For each point inside, so you see the red curve, and it gives a bounded domain. For each point inside the bounded domain, there are 2 representations of this group corresponding. So this complex number is the trace of some element in this group, which parameterize the up to 2 covering, which parameterize the character variety. So for each green point, let's say there is one representation. The R-function representation is over there. The complex hyperbolic group is the horizontal line ending at the cusp point of the blue curve. And the blue curve is the discriminant of the, well, it's the Goldman function of this trace. So if you are in this domain, then some element is elliptic, and you cannot you cannot draw limit sets. So okay, this is almost. Maybe I should. Can I just shut down and turn over some lights? But where? It's here. Okay, it's not. Okay. So this is almost an R circle. And okay, with the techniques that Raphael explained to you, without the fancy arithmetic part in this case, but okay, you can look at the deformation of these limit sets. And you can go, sorry, you can look at the 3D model, but it's just what happens when you are going through the up until the limiting point, well, the Schwarz, the last faithful discrete representation in the actual complex hyperbolic group character variety, then you see that in the limit set, it was a circle, 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 and then at some point there is a pinching. So I could explain that with more time. So if you are fascinated as much as me by this picture, come and we will discuss for several hours. But then you can look at the Cartan map. So this is an approximation of the sup of, well, this sup here, well, of all Cartan invariants. What is, okay, so it begins at 0, and it grows steadily, but in a controllable way. So in fact, in this example, at least, we should be able to do much more than this small deformation property following from positive San Marino-Vinard. We should describe everything. And if you just look at the complex hyperbolic triangle part, so the real line in the character variety, in fact, it grows up. It seems to grow up until hitting pi over 2 at the last point, at the point where someone becomes parabolic. So it is very hard to control this invariant of the limit set, but we conjecture numerically that at least for the complex hyperbolic triangle group, the limit set are slim until you hit the last point where someone becomes parabolic. And I have no time to speak about that, but in some sense, it should help to understand the uniformization of the 8-node complement that you see at the endpoint. And I will stop here.